subtracting real numbers. All right? Let's see how the best way that we can introduce this idea is. Suppose you went into a drugstore down here at the local drugstore and you bought an article that cost, say, $6.75, all right? And you hand the lady a $10 bill. And what she might do is she'll start with $6.75 and then she'll give you a quarter, say, that's $7, and then she'll give you a dollar bill 8, another dollar bill 9, and a third dollar bill 10. So, of course, what is she doing? But she's taking the difference between $10 and $6.75. Is that right? So let me indicate that as 10 minus $6.75 is some number, which in this case is what? 325, such that 675 plus 325 should be equal to 10. Is that right? Okay. And in fact, let's just do one or two more examples like this. 5 minus 3 is that number 2 such that 3 plus 2 must be 5. Okay? Oh, 11 minus 6 is that number what? 5 such that what? 6 plus 5 must be 11. Is that right? A minus B must be that number x such that b plus x must be a. All right? So the difference between any two real numbers, a and b, is a unique real number, x, such that b plus x must be a. All right? Will everyone agree with that statement? You accept that statement? You like that? Okay. And as a matter of fact, that's what we mean by the definition. D-E-F-I-N-I-T-I-O-N. This is our definition of what? Subtraction. Our definition of subtraction. Okay? Our definition of subtraction. As a matter of fact, what I'd like to do is to emphasize this a little bit more, and let's come back to our good old number line. Okay? Let me make an example. Let's make a picture here of a number line. Let's say this is 0, 1, 2, 3, 4, 5. That should be 1, 2, 3, 4, 5 in this fashion. Now, let's take the case of, say, 5 minus 3. And let's look at this as a vector, all right, or as one of these lines with an arrow on it. Now, here is the number 5, all right, associated with that is 5, and associated with what? This one is the number 3, is that right? So 5 minus 3 is that number 2 such that what? 3 plus 2 equals 5. Okay? Everyone agree with that? Let's look at another example. Let's look at another example. In this case, here's 0, there's 1, 2, 3, 4, 5. Well, let's continue now on the negative side. 1, 2, 3, 4, 5. Negative 1, negative 2, negative 3, negative 4, negative 5. Now, in this example, what I like to do is to write 5 minus, in this case, let's write negative 3. All right? Now, there is our number associated with that line with this arrow is the number 5. All right? And let's say now associated with this number is what? There is negative 3. Is that right? Okay. Now, 5 minus a negative 3 must be that number, x, which when added to negative 3 must be 5. So 5 minus a negative 3 is that number, which when added to negative 3 gives me 5. So what must that number be? And everyone says, Chip, 8. All right, so therefore you say that x must be 8. Okay? As a matter of fact, let's look at that example in a slightly different way. Let me make another picture. I think I have room right here. All right, here's 0, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in this fashion. All right, negative 1, negative 2, negative 3, negative 4, negative 5. Now let's come back to that same picture in which associated with this arrow, remember, is the number negative 3, right? and associated with this arrow is the number 5. Now, let's look at this arrow, which is of length 8 and in a positive direction. Is that right? And I think you'll agree with me that we may think of that as this arrow, which is a name for what number associated with this arrow from negative 3 to 0 is what? Let's write it as the opposite of negative 3, right? Because if this is negative 3 in this direction, in the opposite direction we call the opposite of negative 3. And then from here up to there is of length what? That's of length 5, okay? So let's write down here 5 minus a negative 3 is equal to, now let's write it as what? As the what? All right, the opposite of negative 3 plus 5, okay? And as a matter of fact, we have commutativity here, don't we? So how else may I write this? I may write this, Dave said, 5 plus the opposite, well, let's include this as 5 plus the opposite of negative 3, okay? Which, of course, is a name for what? Is a name for 8, all right? Let's continue this example up here, or another example like it up here. Oh, suppose I were to write 11 minus 6 again. All right, 11 minus 6, how do you think I may write that now? How about what? 11 plus the opposite of 6. Okay, 11 plus the opposite of 6. How about 17 minus 12? May be written as what? 17 plus the opposite of 12. Everyone agree with that? Okay. How about A minus B? How may I write this? What do you think? Chip? A plus the opposite of B. Do you think that's true for all real numbers A and B? What do you think about that? And as a matter of fact, we might be able to prove that statement. All right? So let's see if we can't prove it right now. And let's call this idea number 3. And what do we want to say? For every A and B belonging to the set of real numbers, okay, what do we want? A minus B must be what? A plus the opposite of B. Okay? Everyone agree with that? Let's see if we can't prove it. Well, remember how we go about improving something, in which we write the statement here, and we write the reason over here, and we just number our steps and continue from what we know to what we want to prove. Is that right? This is our hypothesis, and then we want to arrive at our conclusion. Now, let's look at A minus B. You and I have been saying that A minus B, by definition, is some number x such that what? B plus x must be A. Is that right? So if this statement is going to be true, all right, what then do we want to say? We want to add, we must prove, let me put it in here, we must prove what? We must prove that B plus, now this element x is unique. Okay? So if I'm saying that A minus B is A plus the opposite of B, okay, another name for x that I can put in here is what?
Real number.
Well, in the case in which I have here, if A minus B, if we're claiming is equal to this, and if A minus B is some number x, then another name for x is what? This is what? B plus x, and now what's the name for x that we can put in here, which we're claiming is true? Which is what? A plus, let's call it the opposite of B, all right? We must prove that B plus this thing that we're calling x must be equal to what? What do we want to show that it's equal to here? A is equal to A. And of course, now there's one reason for all of this, and in fact we're relying directly on the Barb.
Well, you rely on the property of the additive inverse.
Oh, not quite, I don't think. I think we're going right back here to something that I have written on the board. And Sally says, I think we're relying right on the definition of subtraction. This is simply our definition of subtraction that we are relying on here, okay? Well, as a matter of fact, I think it's quite easy for us to prove this statement. Let's see how it goes, all right? There's B plus, let's just rewrite it, A plus the opposite of B, okay, is equal to. Now let's look at this, and there's where we want to go. So you look at it and say, well, I think I can do something in there. Is that right? Like, what? Use the commutative property. So this will be what? B plus, what? The opposite of B plus A. And of course our reason for that is, and Steve says, the commutative property for what? In this case it's our operation of addition, okay? And then of course this now is equal to, and let's regroup our terms, right? And so we'll have what? B plus the opposite of B plus A, and our reason for that is, Ron, the associative property of addition. And of course B plus the opposite of B, Todd said, is 0 plus A, and our reason for that, Todd, is axiom of additive inverse, good. And of course 0 plus A is equal to, and David says, whoops, 0 plus A is equal to, what? Is equal to A.
The identity element is 0.
And we may talk about the identity element for what? For addition there. Or another name, another reason that we could give there is Chuck says 0 plus A is 0. What do we call that?
Axiom is 0. Additive axiom is 0.
Brenda?
Is equal A.
Is equal to A. 0 plus A. Did I say 0 too? Oh boy, it's contagious this morning. 0 plus A is equal to A. Okay? And, well, is that where we want to go? All right, and I guess this would be step 3 and 4 and 5. And now let's just make our conclusion. Therefore, what? A minus B is equal to A plus the opposite of B. And if we had to give a reason for this, what would our reason be? This is about the third time that we've used the same concept here. Chip says the transitive property of equality. Very good. Now, notice how we may write this operation of subtraction. What it really amounts to is writing it in terms of addition. Is that right? Writing it in terms of addition. So let's give a name to this, and as a matter of fact, there's some name here, there's some relationship that exists here between what? Between subtraction and addition, all right? As a matter of fact, if we had to give a name to this theorem, this is a theorem, right, which we have just proven. Any statement which we can prove, we call a theorem. And the name that will give this theorem, the heading that will give this theorem is what? The relationship between what? Well, the book says between addition and subtraction. Let me abbreviate in that fashion. That's the relationship between addition and subtraction. Okay? Now what it will do is it will help us with some of our operations of subtraction here. Sally?
Well, like before you said that whenever you're proving theorems, like you could always be sure that the first statement you put down is the hypothesis.
Well, that's good, all right? And as a matter of fact, I guess what we could have done here in step 1, that is before we wrote down this statement, was to say what? And probably the one statement that I have left out here, Barb says, A and B are real numbers. And as a matter of fact, yes, I guess that would be all that we need to say there. Also, A minus B would be some real number with respect to what operation? What now do you think we can say about that? Give me, you give me any two numbers, real numbers, A and B, and if I subtract those two numbers, what do we end up with? Will you accept the fact that we are going to end up with what? A real number. And what do we call that? That's our property of closure. Okay? So we could have put that in, but I thought, remember I think I said at one point that after a while we'll start to leave out that hypothesis, in which case A and B are real numbers. Okay, good. Let's keep going here and see where this is going to lead us. Let's do a couple of examples, or perhaps more than a couple. Let's look at, again, say something such as, 11 minus 6. Of course, everyone says that 11 minus 6, right, is equal to, and Kirby says 5, all right? Well, let's take the example of 11 minus a negative 6. Now, without having to go through this theorem, or without having to think of the number line, what then is the simpler name for 11 minus a negative 6? Brenda says is 17. Is everyone convinced of that? It's equal to 17. All right, let's look at, say, negative 11 minus 6. All right, Steve says
-7.
a negative 17. And let's try a negative 11 minus a negative 6. And what's negative 11 minus negative 6? Ken says
-5.
negative 5. Is everyone convinced of that? Negative 5, all right? Okay, let's look at, well, let me write down a few other examples up here. Notice now here I had only numbers that I'm dealing with. Let me talk about variable expressions and see what we can say, all right? Well, let's take negative 13a minus 5a. And what's negative 13a minus 5a equal to? What can we say there? And Chuck says
Negative 18a.
negative 18a. Does everyone agree with that? Okay. How about 13a minus 5a? And what then can we say about this? And Jane is equal to 8a. Does everyone agree with that? All right. How about, let's say, what? 13x squared minus a negative 7x squared. What then is this equal to? And Chip says
That would be a 20.
20 what?
X squared.
20x squared. Does everyone agree with that? That's equal to 20x squared. Kirby, is that all right? Mary Lou? Okay. And let's see what other example we can take. Oh, let's talk about, say, a negative 11 a squared b minus a negative 7a squared b. And what may we say that this is equal to? Bob?
Negative 4a squared b.
Negative 4a squared b. Does everyone agree with that? Okay, Barb? Okay, everyone is convinced of this? Now, if there's any question in your mind, if there's any doubt about what your final result is going to be, of course, what you can do is come back and think about this statement right here, the relationship between addition and subtraction, and you might also want to go back and look at it at the number line. But I would rather that you knew it well enough and understood it well enough that you can just write them down, just like that, without having to go through anything else. Yes, sir, Dave?
On those variables there, why would you add them? Because then you have to do your property. You have to multiply 13a before you can add them. Like.
I'm not sure I understand what you mean. Oh, I think you're thinking about the distributive property. As a matter of fact, all right, let's take one of those examples. Which one? Perhaps this one right here, 13a minus 5a would be a good one? All right, let's look at that. 13a minus 5a. And as a matter of fact, when we did these originally, that is with 13a plus 5a, I think what we did was to consider the distributive property with the element a, in which we then had, in this case, 13 minus 5. And then we used the substitution principle to come up with another name for 13 minus 5, which you said is 8. And hence you have there 8a. And what I'm now doing is expecting you to be able to do that in your head and simply come up with 8a, okay? But very good. I'm glad that you mentioned that, because I think it's a good idea to go back every time to your basic property and or your axiom, whatever the case might be, and make sure that what you were doing in sort of a nonchalant and casual way really is correct. Okay? Very good. Now let's see what else we can do today. Let's look at something that, well, all right, how about something like this? Can we say A minus B is equal to B minus A? Well, let me give this as a question. Is A minus B equal to B minus A? And what's your conclusion about that, Brenda?
No.
No. All right, and of course, what do we say? If we were to put this into words, we would conclude what about this operation of subtraction? Sally? Okay, and therefore your conclusion is, Chuck, that subtraction is not commutative, all right? How about is A minus B minus C is equal to A minus B minus C? You think this statement is correct, Barb?
No.
No? Is everyone convinced of that? Because You see, this is now for all real numbers A, B, and C. And if you're not convinced of it, how can we show that in fact this would be false? And Brenda would say,
By finding a set of numbers for which it would be false.
all right, and how many examples do we need? How many cases do we have to show, Sally?
One.
Just one, okay? And I think you would be convinced, or if you were to go through a particular case, in fact, just about any case that you pick, it would be false. How about something like this? Is A times B minus C equal to A times B minus A times C? And what would you think about that statement? This looks like what kind of property? It looks like, Dave, the distributive property of what? Multiplication over subtraction. And what do you think about this? What conclusion can you come to about this case? Anyone have any feeling for this? Let's see, who hasn't said much this morning here? Steve, what would you say about this? Do you think it's true or false? What does your intuition tell you? What do you feel about it? You have any feeling?
True.
You think it's true? Is everyone convinced that? Is there anyone here who thinks that it might not be true? Because for us to prove it, Jane, what do you think? You're not quite sure. Well, I think for us to show that this is true is not to take lots and lots of cases. Remember that, right? What we have to do is to go back and prove it. And as a matter of fact, I don't know that we have the time this morning to go ahead and prove this statement, but I don't think it's too difficult. Because what? B minus C you may call what?
C plus the opposite.
B plus the opposite of C. And just use this statement all over again, which you'd have A times B plus A times the opposite of C. And what's A times the opposite of C equal to? What name have you given that? A times the opposite of C is the opposite of AC. And hence you'll have A times B plus the opposite of A times C. But then that's nothing more but this rule again. And hence that is the rule about A minus B is A plus the opposite of B, this relationship again. And I think you're done in about 3 or 4 steps. Okay? And in fact, I think that would be a correct statement. So here we can say yes. All right? Now, let's see. I think there's just one other idea that we should look at today. Let's go back and consider remember a polynomial. You and I agreed that a polynomial is simply the sum of monomials. Is that right? And let me just write down here the sum of some monomials, plus a negative 8x squared plus a negative 3x. All right? Now notice, it's a string of monomials combined with these addition symbols, right, with a plus sign. But you and I are now learning, by the way, what's the coefficient of x squared in this case? Right here. The coefficient is 3. What's the coefficient of x in this case? Here, Ron? Negative 4. What's the coefficient of x squared here? Brenda? Negative 8. What's the coefficient of x here? And Brenda? Negative 3. Okay? Now you and I have learned how to simplify this. But I'm not going to simplify it yet. All right? What I'd like to do is to use this relationship between addition and subtraction. Let's see what we get. We have here what? 3x squared minus 4x. Is that right? Minus 8x squared minus 3x. Everyone agree with that? All right, I'm just using this relation. Now, again, I would like to ask you, what's the coefficient of x squared here? 3. What's the coefficient of x? And here you have to be careful. And that's the reason why I'm talking about this, because our polynomials are still defined, initially defined in terms of the sum of monomials. And because we are writing this as 3x squared minus 4x, what's the coefficient, Todd?
4.
He says that it is 4. And here's where I have to caution you to have you realize that our definition, we never change definition. Once we decide and once we agree on something, that's it. So now you're changing your definition to say that I can have a polynomial by adding and subtracting. So therefore, I must think of this as a coefficient of negative 4. What's the coefficient of x squared here? Sally? Negative 8. What's the coefficient of x here? Bob?
Negative 3.
Negative 3. Now, let's in fact go ahead and simplify that. 3x squared minus 8x squared is what? Let me call that what? Since I'm going to put it out front, let's decide to call this what? A negative 5x squared. And now here we have what? A negative 4x minus 3x is negative 7x, which we will write as minus 7x. Okay? Ron?
Well, that's using the commutative property to get to that, because you have to switch the 8.
Oh, right, exactly, right. We have used the commutative property. We've used this relationship between addition and subtraction. We've used the associative property. We've used the distributive property. We've used the substitution principle. All of that, bang, we did in like one step.
All right, but you're supposed to use the associative property,
Oh, very good, very good. Ron says, but we're using an associative property, but am I using it with respect to subtraction or with respect to, Bob?
Respect to addition.
It's in with respect to addition. Again, I'm thinking of this as 3x squared plus a negative 4 times x. I'm thinking of it that way, but it's easier for us to write it in this fashion. And as a matter of fact, it might take you a few days to get accustomed to writing polynomials with this dash symbol in it. You're going to want to write it with plus and then parentheses. But that's all right. I don't mind that as long as you know exactly what you're doing. And then you're going to shift over into this symbolism right here. Okay? Well, I think that's all that we have time for today. So let me give you your assignment.